So I wanted to talk a little bit about related rates because that's one of the units, one of the topics in the unit that we're working on. And related rates, the key idea is that you can think of each of the variables in the problem as a function of some other thing. Usually it's time. So a classic example, really the classic example of a related rates problem is where you have something like a wall. You have a ladder leaning against the wall like this, and perhaps the ladder is falling down at 1 foot per second. So the height of the ladder, which we could use the letter y for, is not a constant anymore. It's actually a function of time. I don't know what that function of time is. All I know is that at one point it is moving at 1 foot per second. It'll speed up because of gravity, but we only know that one moment. If the top of the ladder is going down, then the foot of the ladder is moving outward at some related speed. That's why it's called related rates. And so the question is, what is the change in your x, the foot of the ladder's distance from the wall, in relation to the change in the top of the ladder moving up and down? So if we have, say, a 15-foot ladder, and let's say that at some moment it is 12 feet above the ground, and if you do 9, 12, and 15, you get a full right triangle, so I know it's possible for it to be 9 feet from the wall, 12 feet high up the wall, 15 feet. And we're just going to assume it's moving 1 foot per second down. So what you do with a related rates problem is you set up your base equation. And when you do this was confusing to me as a student. I'm tempted to just plug in 9 and 12 and 15 because I know that the moment I care about involves x equals 9 and y equals 12. So I'm tempted to just plug them in at the beginning. But the way that you do a related rates problem is first you think about it in the general situation and you take a derivative to figure out how are the rates related at any moment in time, and then you plug in your particular information. So when you do this, I'm going to remember that x and y are not just regular variables, that they're each a function of time. And so I'm thinking of this like implicit differentiation or like the chain rule. So when I take the derivative of x, I can write 2x times x prime. When I'm doing related rates, I usually like to write dx dt to be really clear that my x value is changing with respect to time. And same idea with y, 2y, and then chain rule times dy dt. Some people get confused also about what to do with the constant. A couple ways to think about it. One way is to think, okay, the derivative there is just 0 because it's a constant. Another way to think about it is it's times d, let's say the hypotenuse is the letter c, right? Then it's times dc dt. Well, if the ladder is 15 feet tall, 15 feet long, it doesn't matter what angle the ladder's at, the length of the ladder is not changing. So dc dt is always equal to 0. So if you did set up this original equation here, and if you had put, say, a c squared here, then you would get here 2c times dc dt. But because the ladder is not changing its length, that part equals 0 anyway. A couple years ago when I was teaching, somebody was talking about, we were kind of joking, but they were saying like, what if it was a collapsible ladder? Well, if it's a collapsible ladder, then you can handle that with what dc dt is. You would just need to figure out at what rate is the ladder moving in or out. At this point, it's just plugging in what we know and solving for the piece of information we don't know. So 2 times x equals 9. So now I plug in the particular value. dx dt is what I don't know. Plus 2 times y times dy dt, which I do know, is 1. But it's actually negative 1. Think about why it would make more sense for it to be negative 1 in this situation. The y value is actually getting smaller. It's decreasing. So the ladder's falling down. If I was pushing the ladder up against the wall, then I would have a positive y, dy dt. So here we get 18 dx dt minus 24 equals 0. So dx dt is 24 divided by 18. Dividing by 6 gets you 4 over 3, and that's in feet per second. And so if the top of the ladder is moving down 1 foot per second, then the base of the ladder is moving out slightly faster than that, 4/3 feet per second. Kind of hurts my head to think about how those two things are moving sort of at different speeds, but that's just how it works with those particular angles. All right, that's it. Please let me know if you have any questions. Happy to help out.